nice tribute in the beginning, Tony. It's, sad to hear any, giant in mass spec, to be passing on. So it's good to remind, where, our background and where we come from. But so very nice. So, thanks for the opportunity to talk today. I am a part of this community. I recognize maybe because I had a harder time finding the link that maybe I'm not getting some of the updates from this group. So, maybe we can figure out a way or I need to figure out a way with LinkedIn to kind of get some more of the updates. But ultimately, thanks for the opportunity. So, ultimately, I'm John Stutzman. So I started my academic career at a small school in Pennsylvania. Like I'm in college. I finished up there in 2009 and moved to Purdue University. Inherently had a strong interest in mass spec. I had no idea what I really wanted to do. But I kind of played statistics and said, Purdue had a lot of subject matter experts in mass spectrometry, so the likelihood that I would get with a group there would be high. So in 2009, I started with the McCluskey group. And so I spent most of my time doing gas phase ion chemistry. And so Scott's area is in ion. And early that period was where he was starting to do covalent modifications in the gas phase. So I spent a lot of time on shift base formation, along with getting the group interested in ion chemistry with lipids. And so that's been a pretty productive area. And it was kind of right in the beginning of the high interest with folks like Blanksby and some of the other folks with doing ion chemistry of lipids. So after that, I started at Dow Chemical in 2014. And so I've been a part of their analytical science department for the last 10 years. I just hit my 10-year anniversary a couple years ago. And so really my focus at Dow has been, being a mass spec subject matter expert. And so I spend most of my time doing structural elucidation. And so my focus has been more on small molecules. So I publish a lot on polyols, but I actually spend most of my time characterizing small molecules, especially in the context of catalysis and polyolefins. And so that kind of lines up to my next part where I talk about, what are some of my interests and that kind of how it connects ultimately to some of the papers that I publish. So my interests are in ion chemistry. So I'm always trying to figure out ways that I can change, the ions after they've been ionized or change them in some way to get new information, modulate the fragmentation, help the characterization. Areas in ion activation to dissociation. As a structural characterization person, CID is a great tool, but, other types of, tools in our toolbox are really important to give complementary sort of information. Most of my papers involve, some aspect of coupling, advanced mass spec to chromatography. And so another aspect of my focus has been really separations MS. I like to do hardware modifications, so we'll talk a little bit about today about some of the, the more simple ones. I'm kind of used to in grad school where we build an instrument and do all sorts of crazy things where we really can't do that anymore in industry on some of our commercial instruments. Last thing I get interested in is catalysis and life cycle analysis. I spend a lot of time trying to understand what happens to catalysts over their lifetime and, how they are in our products, the safety, the toxicology. So the last part I'll mention before we move on to maybe more of the publication is recently I've taken on some of the global responsibilities for mass spectrometry at Dow, so mainly aligned to our department. And so a lot of the internal strategy, capital decisions, also external partnerships with vendors, UPIs, or not UPIs, external research labs, national labs, academic groups, vendors. So, if there's something that you see here and, we potentially want to come up with further research or some sort of collaboration, I would be a great person to at least get the ball rolling. So I wanted to mention that. So I'll quickly move over to the paper that we have today, so that we're going to talk about. So I'll say, stop me as we go through this. If you want me to zoom in on something, feel free. As I mentioned before, being in a corporate sort of atmosphere, it can be hard to create slide decks in a short amount of time. So it's really kind of nice to walk through this just as a paper. But as I said, stop and feel free to ask me questions. So as we start to look at this paper, the title is Online Bipolar Dual Spray for the Charge Reduction and Characterization of Complex Synthetic Polymers. And I get characterization, complex synthetic polymers, they can mean a lot of different things. So I'll try to illustrate, what I view as some of these problem solving during this presentation. So ultimately, as I mentioned, my interest comes to charge manipulation, problem solving in the context of mass spectrometry, but also with separations MS. And so really, in order to do some of these, ion chemistries or ion manipulation techniques, you really have two options. You can do in the gas phase, or you can do kind of at atmosphere. And so, as I mentioned, it can be very challenging in a industrial setting, along with having commercialized instruments to be able to modify them to do things like ion chemistry, ion molecule chemistry, just because of the software constraints, some of the safety, some of just the practicality of doing this. You don't want to take an instrument that's collecting data daily and ultimately kind of modify it to not allow it ultimately to collect data in that way. So we need to find ways to do some of this chemistry without affecting these instruments on a daily basis. So, where I'm starting here is kind of at the end of the story. So I'll try to quickly, maybe give a little bit of context before I get into this. So a couple of years ago, and it's I guess it's kind of a shameless plug, but really the idea here is that polyols, whether they're EO, PO, no matter kind of their molecular weight, if you try to analyze them in a separations MS way, so not thinking about MALDI, but thinking about LCMS, many times you're going to get multiply charging, okay? And, low molecular weight, not a lot of high charge, you can probably get away with it. It's a little bit more complicated, but ultimately it's still kind of challenging to go through even 2,000 to 3,000 molecular weight. So when I first joined Dow, the idea is how can we potentially do some sort of charge reduction in the context of an LCMS experiment? So when I first joined, there was a methodology related to polonium chemistry. And without going too deep into it, it's basically a charge neutralization source, and you can tune it so that you can essentially get all of your ions from multiply charged to singly charged. Now, most of the distribution has been neutralized, but you're kind of sampling the small context of, +1. And so we developed this methodology of coupling charge reduction to complex mixture analysis, especially with polyols. And it was pretty successful. It was a fun investigation. The problem is that you guess when you have a polonium source, it's radioactive, you have to buy it somewhere. You have to get it shipped in, you have to get approval through the nuclear regulatory department. You have to have certain levels of testing done so that you're not leaching out the radioactive source. And, generally people feel uncomfortable, using these things. They have a half-life of 138 days. So when you start to think of, hey, I may have to do 2 to 3 analyses that utilize this technology over the course of a year, by the time you want to go use it, you have to order a new one. And so ultimately, this really wasn't a long-term sort of ability to kind of manipulate the charge state distribution of polyols to facilitate, the characterization.
May I just ask a quick question here? If you can just tell me very briefly, what's the mechanism behind this charge reduction?
Yes. So the way that this works is it sends alpha particles into the ion, like in the local area of the plume and atmosphere near the electrospray, and that will interact with solvent molecules, gas molecules. It will eject electrons. It has this cascading effect that will create like a bipolar plasma. So you'll have positive charge, you'll have negative charge. And so those ions then interact with your desolvated ions that you've made, okay? The mechanism of exactly what ions you make from the atmosphere, the solvent that you're using in the alpha particles is not completely understood, but ultimately that process is the way that you kind of do that charge stripping. So you're doing ion-ion chemistry in the ion source.
Okay, and so would you have something kind of equivalent if I put, for example, a dart spray in the source, like which is actually emitting helium, which is basically alpha particle? Do you think I would have the same kind of, or I would like maybe some energy to do the same transaction?
You would have to. So I don't know. I don't use Dart. I don't know. Does I think Dart also uses a AC source, right, to create some sort.
And the helium still has its electrons. Sorry for jumping in. It's not alpha particle. It still has its electron. It's metastable helium.
Yeah, metastable helium. So, but like, is it different from alpha particle? It's not a helium.
Yeah. So alpha particle is the naked helium. Naked, just
okay. I see. Okay.
And the energies are gonna, the energies are gonna be
probably very different.
Widely different.
Yeah. Thank you.
So I don't want to. We could talk all day about this. I just kind of wanted. It's this kind of the pretext to the paper, because I didn't just want to jump in and say, how did you get here, or why did you do this?
Can I ask one more question though, because I have heard from some ion mobility experts about using polonium sources for large particle ion mobility, some non-ion mobility mass spec, and they prefer using these polonium sources as well because it does convert well with large ions. Have you been able to attach these polonium sources to say Thermo's high mass instrumentation to see if you can get really large polymers to ionize well with these polonium sources?
So I've never attached it to a the the UMHR instrument. So on a QTOF instrument, I've been able to get up to about 10 or 11,000 utilizing this. I recognize that that's pretty low, maybe compared to what other folks have looked at historically. That being said, I don't see a reason why you could not do it on the UHMR. However, from a ion chemistry standpoint, from a ion transport and detection, I think that's where it fails. So these UHMR are used to analyzing, 50, 60 charges on like a virus or some sort of, quaternary protein structure. And ultimately, they have enough kinetic energy to make it through. So just on a straight regular tune, UHMR that you get from Thermo, I don't think it's very likely that you would detect or transport it. I think they would be there, but it would be hard to tune it and get everything right. Now, if you tune what's that?
That's a good point on the tuning part. Sorry, I hadn't considered that. Thank you.
Yeah. So so I'll move on. So as I kind of said, this was, one part was it was a nice technology, but there were some caveats to it, right? So then Jenny Broadbelt in, I think it was like 2016, 27, or maybe even a little bit earlier, she started working on something that she kind of termed dual spray, where she was taking oppositely charged emitters, and they were trying to replicate some of Scott McClucky's work related to shift-based chemistry and some of the other things that was aligned to my work, where they're basically making long-lived complex and droplets that were traversing to the gas phase that you could then do the do the rearrangement chemistry inside the mass spectrometer. So when I started to see this, I said, man, there's got to be a way that we can do some sort of charge manipulation, some sort of chemistry. So the initial sort of interest that I found with this dual spray technology was, can we charge manipulate or ultimately charge reduce some of these polyols by this methodology? And so the quick answer is yes, we can. And, you know, we wanted, in this paper, I tried to understand what is kind of the underlying mechanism, or, you know, what's going on. And what we were able to find is, you know, essentially when you put in anions at a higher molarity or, you know, concentration than your analyte and then your additives, you find that you can basically destabilize the process of, you know, ammoniation of PEG during ionization. And that's by using anions that will either pair with the ammoniums in solution or in the droplet, or interact, you know, with the polymer that has an adducted ammonium and destabilize that as it goes through the ionization, it goes through the droplet evaporation phase. And so in this study, we, you know, devised all these different experiments with like salts and bases and different solvents to really demonstrate that you could do this. And really what, you know, this has kind of been observed, you know, by Brian Chait and also Dick Smith, where that if you do electrospray with a high concentration of acids, you can manipulate the charge state of proteins, okay? So we had seen it somewhat in an analogous sort of situation with, you know, different analytes with one sprayer. So, you know, ultimately we were able to kind of show, hey, you can do charge manipulation of these. And what's important is observing new charge states. So you're not just biasing the front plate or biasing it in some way, and you're sampling higher molecular weights. You know, this is truly your, you know, changing the electrospray process, the ionization process to observe different charge states. So that was kind of where we were prior to this paper. And so my interest here was, how can we, is it one possible to do this dual spray charge reduction in the context of an LCMS experiment? Are things like water or mobile phase conditions going to really kind of, you know, not allow this? So a lot of the initial studies were done just purely in methanol. And so, you know, the first part of the paper is trying to understand, you know, is this applicable? So I'll kind of go to the first figure here to kind of give you an idea of what we've done. And so I think Paul Hutchins is on the call. Paul helped me make a lot of these figures. If you go to my older papers, the figures are not so nice. Yeah, I did my best, but Paul's really great at devising some of these. So I want to give him a kudos to that. And so essentially what we do is we have some sort of analyte that's coming in with LC, okay? And this is based on an adjuvant ion source where they have the dual spray or the dual ESI, kind of the master flow or the LC, or, you know, the infusion would be kind of on the top, orthogonal, you know, to the inlet of the MS. Since they're using a TOF system, they like to use ultimately a reference ions to kind of calibrate. So what happens is this is kind of the reverse to what I'm used to, where they hold the electrospray capillaries or emitters at neutral, and the front plate is the kind of the applying electrospray voltage. So what we have to do is kind of isolate this electrospray emitter. So you pull out some of the conductive portions. The outside of this, I think, is made of PEEK. And what you can do is connect an external power supply, which we purchased, and then you can apply, you know, negative voltages. So that ultimately, and when you're electrospraying in positive mode, you're ionizing your polyols, and then in your negative mode, opposite, it's about a 30-degree angle. You're electrospraying in the negative mode your reagent, in this case, which are acids. So kind of the experiment that we're starting here is the reagent is flowing in at about 30 microliters per minute. It's methanol with, you know, 1% formic acid. Again, we want to have high acid concentration to be in excess of, you know, your analyte ammonium cations and also your analyte. So then from this side, from a chromatographic side, so we're moving away from just infusing things in the last paper to now doing chromatography. And so essentially here, what we're doing is we're using a 6560 platform. So that's their Agilent's ion mobility, and it has a 1290 HPLC on the front. And so essentially we put on a typical C18 porous shell. So that's a core shell technology. It's a bit better at separating things. We create 2000 ppm solutions of polyol and methanol. We inject it onto the column, which again I mentioned was a porous shell. I think it's 3 by 100, 2.7 micron. We have mobile phases of ammonium formate and water as A, ammonium formate and methanol as B, and we do a linear gradient, basically 50 to 100 over 12 minutes. So pretty standard chromatography. The flow rate initially through the column, the master flow rate is about half a mil a minute, so 0.5 mils per minute. The one thing that we need to do here, I mentioned that the reagent flows at about 30 microliters per minute. We need to split this down, because if we run substantially higher, it's shown that when the master flow rate or the analyte is substantially higher than the reagent, we can't do the chemistry. Okay. So we split from 500 microliters per minute down to, I think when we calculated, it's about 5 microliters per minute. So we're vast excess not only in your reagent concentration, but also kind of the spray volume too. We have noticed that I have done experiments where you can go up in flow rate, and we mentioned this in the paper, as long as this exceeds generally what the LC flow rate is or what your analyte is, the chemistry has demonstrated to work. So let me see if there's anything. So the way that we split it, we have a home built splitter where basically you have a long leg with a larger ID, you have a shorter leg with a smaller ID, and based on pressures, you get a specific flow rate, which ends up being 5 microliters per minute. Okay, so this is kind of the setup. I think the nice thing, the last comment I'll make is, to modify this instrument, but in a way that you can do specialized chemistry, but then in the afternoon you can also do your normal experiments, is really important, because we don't have instruments that we can necessarily just completely devote to a type of chemistry like this. So it's important from an industrial side that in the morning we can be doing one type of experiments, dual spray, and then a couple hours later we're doing something else. And so setup to tear down takes like 10 minutes. So it's very quick. The one last part I'll mention is we do tune the instrument to have a higher low mass cutoff so that we can observe higher molecular weights. So we're tuning it really so you're not going to see things below 500 M over Z, which we're not really interested in. And so just recognize that we're tuning this instrument to kind of bias towards higher molecular weights.
John?
Yeah.
I have a question. When these sprays are kind of interacting, do you feel like they're the sort of wet droplets are interacting, or are they far enough apart where it's more like almost a gas phase almost interaction?
Yeah, so my feeling is that these are micro droplets that are interacting, that are fusing together, where there's an interaction in the desolvating droplet. I don't observe these as being ion-ion chemistry in the gas phase. So this is pretty distinct from the polonium source. I spent a lot of time in the first paper trying to understand that. And I think one of the key experiments that demonstrates it's a micro droplet is that you can go up to higher flow rates, like several hundred microliters, and these things will ultimately continue to do the chemistry. And most of those droplets are likely not going to be completely desolvated by the time that they make it inside the heated capillary.
Hey, John, a quick question, I guess, on your spectra on the right. I guess this is where you've done your charge reduction. So you have singly, doubly, triply, quadruply charged.
Yeah.
So these are, I guess, 7,200, peg. what kind of information are you able to get out of the spectra, especially that one on the right with all that different? I mean, you still have a lot of charging that's present. Are you able to still get the number, average molecular weight, see the different end groups, any side products? Because that's still going to be a complex spectra to have to deal with.
Yeah, so we'll get a little bit more into that later when we have like an application standpoint. So in this standpoint, yes, you can do things like you know, MN, MW. You can utilize the you know, the accurate mass information to back calculate, you know, what the end group is. There's maybe one or two things that you could do a little bit better. If we had MS capabilities at higher than like 2,000 or 3,000, you could start to fragment these and interrogate the structure a little bit more. But you can certainly, if you have mixing in like EOPO, you can determine that, but we didn't work with those specific things. I will mention when you get to about 2,000 molecular weight or M/Z, you start to have challenges with the software and ability to accurately assess, you know, 5, 6, 7, 8, you know, their intensity. So I would say, you know, as long as there isn't severe overlap, you can kind of pull that information, but it starts to struggle generally.
Yeah. How would you calculate M sub n from that? Which of these charge states are you going to use to do that?
Yeah, so I would use I've used Polymerics and Sierra.
Yeah,
and
software, but I mean, but which charge state are you going to use to do that though?
I don't know what you mean.
You have a singly, doubly, triply, quadruply, and then you have an unknown. I mean, so how are you going to calculate the M sub n from that?
So what I do is I go through and I calculate what each charge state is. So typically what I do is I take a average charge state distribution. So I'll take the relative abundance of all the signal from 1 plus, 2, 3, 4, 5, 6, etc. Go through, bin those, take the average charge state. But from an MN, like I said before, you can use computer software to go through and calculate those, but as you start to have higher molecular weight, the accuracy goes down.
Yeah, but essentially, when I actually did these studies comparing, I did a different approach. Essentially, I did a controlled ionization, so you still don't have control on the ionization. But essentially, what you have to do is you have to take into consideration every charge state, every single charge state. If you want to compare that with the MN capabilities of something like MALDI, and then we would see what MALDI was in very much agreement with GPC. So that's essentially, if you were to select one out like M singly charged, it's going to be way off. Same with the end groups, because it's the higher molecular weight portion that's going to be like the quadruply charged. It's so that you're going to miss a portion if you don't take every single charge state in consideration. So that is definitely one of the things that you have to consider when using this type of approach.
Yeah, and I don't, you know, to your point, I don't necessarily view this as trying to get a really accurate MN or MW. You know, it's an important aspect of that, but it's not maybe the most. It's not necessarily the sole purpose of this. And you know, I think there's other, like you had mentioned, that there's other better techniques to go about that. Maybe that, hey, you know, MALDI gives a better representation because you're not, you know, overly represented in higher charge state. Also, we're manipulating the charge state. So I think you'd have to do more studies on, you know, how that tracks over the course of molecular weight and its ability to charge reduce. So yeah, I think that's a really solid point. I think I saw Chris raise his hand.
Yeah. Yes. Is there any reason why you used ammonium instead of sodium?
Yeah.
Yes. So we find that you know, often sodium has negative effects long term on, you know, both our HPLCs, but also our instrumentation. So if we're running, you know, quite a bit regularly, so like every day, we notice that, you know, sensitivity drops over time. You start to get buildup, etc. So I find that ammonium is, you know, a pretty volatile salt, and ultimately it has a great charging ability for a lot of these polyols.
Yes, that's nice. I mean, this is acid-base chemistry. And I mean, I asked because my follow-up question is that then traditional way to reduce charges was to add a super base like,
Yes.
I forgot now,
PBU
like
is a big one, yeah.
guanidine-like super bases,
Yeah.
and you can have essentially the same effect. Obviously,
Yes.
for them to work, you need protonation as or ammoniation as the not sodiation, because then you would have to find something that has high sodium ion affinity to remove the sodiums. So did you compare your results with published results that reduce the charge just by adding a super
Just
base?
chemical, yeah.
Yeah, so I haven't compared this directly to adding some of the bases. So this is my rationale, okay? And take it for, face value of, again, kind of using this in the context of a daily driver instrument, putting molar or millimolar concentrations of amines that have substantial molecular weight. I'm not saying like if it's, like trimethylamine or something like that. But if you have to put in substantial amine concentration at, a molecular weight that your mass spec is going to observe, you will be successful in charge reducing, and observing lower M over Z ions. The problem is you're going to have no sensitivity in the long run. If you're
going to contaminate the instrument.
Yeah. So
this triasa bicyclononan and or diasa. I mean, please correct me. The bicycloundecan. Those are very small molecules. Actually, they look like arginine side chain. They have this guanidine in them to be very super basic. So they're not very high in mass. But you're right. They'll stick in the instrument and they'll contaminate the instrument.
And you don't even have to be able to observe them. If they're low molecular weight, they suck up charge, and they just, if the context is if you want to do something else, it's not a digital effect. You move to this experiment, you move to the next, you always have that hanging out. So that, I think the other aspect of it is, the adding amines is a great way to quickly identify those things. I'm trying, my interest is, again, from the ion chemistry side, but also trying to think of ways that this can be, not as as negative or disadvantage to your instrument.
Good. Thank you. Very nice.
Yeah, and one last thing, we did look at like lithium chloride and some of the experiments in our previous paper. So there are some more experiments that we talk about how this works with like lithium and more of your traditional salts. Okay, I think, Terry, did you have a question, or do you need me to keep going? Because we're at 11:43 and we haven't even gotten to the meat of the paper.
Go ahead.
Yeah, so then maybe you can keep going, then I can have a question later.
Yeah.
No problem.
Okay. I have a couple minutes after that we can stay. So, first thing is, we look here and we see, this is just direct infusion, and we're kind of demonstrating here that, hey, this works, right? So it's something like the average charge state here, I think, is 8.1. You can go through and calculate what that average charge state is. And then you can go over and introduce your formic acid under the same conditions, and you can now see that, the shift in charge state, where now you're seeing like an average charge state of 4.4. So this is all good. This is kind of reestablishing some of the previous technology that we did in the last paper. So when we look at, moving towards now doing it online, so this is the total ion chromatogram from just the LCMS of PEG 7.2K, okay? So we look at that, and ultimately we can see, hey, we're observing, multiply charging. We're seeing some of the lower charge states. I will mention this star here. This is related to fragmentation of the PEG. So the ion mobility that we have, you can't set up fragile ions when you go to a higher molecular weight tune function. And so these will actually cause some ion activation through the ion funnel in the very beginning. I actually was kind of paranoid that I was kind of tricking myself. So I tried it on another instrument, and surely that intensity went substantially down. And so pretty confident that a part of that ion mobility section is kind of causing some of this. So just recognize that this isn't going into the calculations, and this is kind of like an artifact of the measurement. So then when we start to do the charge reduction, or the dual spray of this, we can see that there's a shift in average charge state to 4.4 from 8.2. And so these are under the same mass spec conditions. There isn't a change in the low mass cutoffs. I will mention when we look at this, there's increased signal to noise on this, along with there is a diminishment of signal that is kind of inherent to this measurement. Ultimately, where this has kind of been seen before is when you start to introduce a lot of small molecule ions and salts and different things, you tend to get low M over Z clustering, and that kind of causes some ion suppression in your higher molecular weight species. So this is consistent with what we observed in our previous paper, but we're able to see, yes, we can actively lower the charge state distribution of these pegs by in the context of an LCMS experiment. So I guess the comparison that we have here is between the LCMS, where we see predominantly, I think it's 4.4 versus, and the lowest charge state we see is 2. If we go up here in the direct infusion, we see, I think it's 3.5, and we also see +1. Okay, so the question is why aren't we seeing as significant charge reduction in the direct infusion versus the chromatography? And so with the direct infusion, we're completely working in methanol. We're not adding in aqueous components to it. And so once you start to do chromatography and we get to this point, what we recognize is we're about an 80-20, 80 methanol, 20% water. And so you can actually go and do direct infusion of an 80-20 mixture. And so let me see if we have this here. If you do that, so this over here is in the supplementary. If you look at the 80-20, you see almost the identical composition. So like I think the charge state distribution matches it almost perfectly, and you're seeing no +1 like we observed before. Okay, and so what's the cause of this? So when we think about like a methanol solution, or a purely organic, that's not that's kind of a bystander in the micro droplet fusion kind of like mechanism. So when you start to add in things like water and you're electrospraying, you're making protons, you're making potentially hydronium ions. So now you're introducing additional competition for the interaction between ammonium cations and the formate anions. And so I hypothesize here that essentially you're introducing more competition for that formate charge. And certainly it is in excess, but there's something going on here where you're no longer having that pure interaction between your formate and your ammonium cation. So that matches to say that it's more of a solvent composition than it is related to something with the instrument or coupling with chromatography. So let me see. Okay, so that was kind of establishing the ability to do that. We had some other experiments about, introducing nebulization gas. That's another aspect of it. I can lead, if we have questions later about that, we can talk about it. But one of the things I always, as an analytical chemist, it's great to do some of these more fundamental, like, hey, we can manipulate charge, right? I always kind of like to say, where is this worthwhile? What's the use case here? So I had been interested in, some functionalized pegs, are there isobars? Are there ways that we can do things? And so one of the things that I got interested in was this bis pegamine. And like functionalized pegs have all sorts of uses, across many different industries, like in biomedical applications. We also can think about like cosmetics. But when we start to think about, a certain molecule called like peg-bisamine, or it's peg-bisamine. So the way that they make this, is you essentially have some sort of peg. You introduce a really good leaving group to react on the ends, and then you treat it with ammonium hydroxide or some sort of a basic ammonium solution, and you can functionalize the end of this. Okay, and so one of the things that as an industrial chemist, you try to think of like, okay, what are the byproducts? What are the impurities? Because not only do you want your process to be, high performing, you also are concerned of what sort of things are potentially present, that can be passed on to the environment or the consumer. So, thinking of ways that, what are the impurities that are present? And so knowing that, there's a synthetic route to this, there's likely going to be some sort of impurities. And so this is hard. It's hard whether you're doing LCMS, whether you're doing NMR, whether you're doing MALDI. It's challenging, especially when things are maybe low molecular weight and you have ion suppression, or they're close and you have, they're high molecular weight, so they're isobaric. Their envelopes will overlap and be, kind of isobaric in that sense. So I thought this would be a good way to say, okay, how can we do some maybe potentially impurity analysis of something that's not a major component? And so, the first step is doing some of this dual spray and trying to observe, can we see any sort of impurities? And, when you look at this, again, it's complex. This has amines, so now you have a combination of protons and you have a combination of ammonium ions. And so I try to, leave this generic, not to insinuate what the charge, we can figure out what it is, but, we observe a distribution here, and you can kind of go into further interrogate this. You can get a pretty good idea of what their, the empirical formula is based on the accurate mass and isotope modeling. And, what we can pull out here just looking is, okay, we have some, in the 2+, we have, protonated versions, we have one protonated, one ammoniated, two ammoniated. And so as we kind of look at this, it's complicated and we can't necessarily pull out any impurities. So the next part is how would this respond just by doing LCMS? And so we can put this PEG bisamine, we can look at this over the course of an experiment, and you can rapidly, I think sometimes people fall prey to sum the whole TIC and say, okay, this is what it looks like. But, kind of rapidly going through little periods of time is what we did here, because I think that gives a more holistic view of what you're looking at, because I think it's unfair sometimes to do the whole thing and just say, oh, we can't interpret this. And I think this identifies that this is complex enough that even with chromatography, you're not really able to go in and pick out anything beyond the main component. I will say, as a separation scientist, along with mass spectrometry, that back shoulder was like, whoa, what's that? Because it has something. And so if you look at this part of the distribution, it is consistent with the higher part. So later I'll kind of address that, but I'll try to head some questions off by saying it looks very similar to the front distribution, and because the question could be, is this, a separation of, PEG or something else? But so the next part was looking at the dual spray in the context of this experiment. And so we're able to perform that. We have an idea of what the chemistry is. And so when we start to look at little snippets of the chromatogram or small mass spectra, what we can start to see are, there's smaller distributions that are present beyond the PEG-BA. And one part is, we can look at this from a complete unknown standpoint. What is this? The other aspect is we know what the chemistry is. And so that can help guide us to some degree of what's going on. And so when you start to look at, the predicted accurate masses of these things, you calibrate this based on known peaks. You start to model, what the empirical formulas are. You can start to pick out, hey, this is, tosylated end group here, so this the leaving group hasn't been removed. And you can see that as doubly, triply, and I believe there's some quadruply charge here we just didn't point out later. You can also see, half of the reaction where you were having amine on one side, but not on the other. We can see that throughout. And then we can also see some of the starting material here, okay? And if we pull up the, kind of the controls throughout, you can walk along the chromatogram and see the increase in molecular weight. And you can also see, the different distributions. And so we see here, higher molecular weight, we can still see all the different impurities. What's important here is, we're not getting, I'm not saying we're doing the best chromatography ever, right? We're not getting baseline separation between, all the different components, okay? And that's not really the intent of this. But there is enough separation of, the different peg, functionalized pegs versus molecular weight that it allows you to get that a slightly chromatographic resolution along with the decompressing of the mass spectrum that we can go in and start to characterize these things. And so one of the additional things that we kind of supplied here that Paul helped me with, in addition to many other things, was kind of modeling these, because as you'd expect, these are high molecular weight, which is typically not, in the wheelhouse of like a QTOF instrument. We want to make sure that they're also low in signal, so you're kind of summing a lot of different signals over the course of the chromatogram. So reasonable mass error for this extended version of the mass spectrum. Pretty good representation of the isotope envelopes. Overall, what I try to say, the empirical formulas, the AccuRass is consistent with these. We also have you would say the patent information to show this is how it's done for these certain products. So all of this together gives a really strong case. It's this, okay? My hope would be that we could go through and do MS of some of these. There's really two challenges that come with that. One is, we are limited in our mass selection of our quad. There's, problems with intensity. Would you be able to, select and then get enough signal? Because these are lower, we're losing signals, they're low intensity ions. So there are some challenges related to doing like an in-depth characterization, but with, the isotope modeling, the spacing, the charge state, along with the accurate mass, we can get along with the chemistry, we can get a pretty good idea. These are consistent with these process impurities. So
for MSMS, though, you're going to be far better off if you can get that to protonate or maybe with lithium than trying to do ammonium catenization. That's going to be hard to do, especially with high molecular weight pegs.
Okay. No, that's a great suggestion. And ammonium versus lithium, what do you typically observe? Do you see more N groups?
Well, if you've done a lot of structural elucidation, you should already know that ammonia is going to pop right off. You have lithium, especially protonation. Now you can get a lot of. I mean, just look at the literature; it's well reported, John. You should know this.
I think the metallated one going to give you more interpretable spectra than the protonated ions. So that's one. And the other thing is what Tony said, that the ammoniated ones are going to lose ammonium now, and so you're going to form the precursor ion minus ammonia. And so you need a kind of an MS3 experiment to be able to get the good fragmentation. So,
yeah, but then like the system is also providing a lot of energy, as John showed. So like in the end, you're producing an M plus H, which itself fragments.
Yes, there'll be
fragments
correct
in the same MS2 step. You don't need to reselect the M plus H. The M plus ammonium is a way to protonate indirectly, and then the M plus H is fragmenting.
Just increase the collision energy, in other words. That's essentially what theory says. Absolutely, yes. Especially we found out that the higher the mass, the more of the consecutive fragmentations you see. So
I have a quick question here. Like, so you actually showed some TIC with without the dual spray turn on. When you have the dual spray turn on, the TIC looks the same. You're just losing signal, but it's the same profile, or you have a different profile and different relative contribution of the different parts?
Good question. Most people don't ask about that. So yeah, so what we're showing here is the best case scenario for like, you know, a TIC with LCMS. If you go and you look at a TIC from when you're looking at the dual spray, you will see, you know, lower intensity, and along with the signal stability sometimes is not as good. And you see that in the supplemental, where there's, you know, when you're going to lower signal, higher molecular weights, and along with the dual spray, your signal intensity just, it goes down, but also some of the stability, there can be some challenges. So overall, the TIC does not look like this. It looks, you know, a lot smaller and maybe a little bit more jagged.
John, I just wanted to mention, like, while you mentioned the separation isn't the best, I mean, another thing that really would help, in addition to the charge reduction stuff that you're doing, would be to try to improve the separation. I mean, there are things that you might be able to do to pull some of these things apart, you know, with different organic solvents like acetonitrile versus methanol, and maybe even changing pH because you do have amines and whatnot. But the other thing I was thinking was that if you actually are involved in looking at the synthetic pathway here, then if you had the precursor sample, like the thing with the tosyl groups on it, then you could also help to confirm your assignments by looking at that precursor material and saying, yeah, we're expecting to see maybe mono and di having that or aromatic end group on there, and that could potentially help you make your assignments in your final product.
Sure.
That's a good point.
Yeah,
Good point. I
something
think
too, like I'm sorry, please go ahead.
No, that's okay. I was saying that was a good point to use a reference. Go ahead, Thierry.
Yeah, like I was just thinking, like, indeed, if you're able to have a better separation, then you can do, like, instead of doing an MSMS with the quad, you can just do an all ion fermentation, activate everything in the, I mean, just increasing the energy of the phenol or the AMS to voluntarily fragment the ions. And then even if you don't know which precursor gave the fragments, if they all belong to the same distribution, they will still give you some interesting ions in the low mass range. So you can activate still a 5K or 4K ion. It will fragment into small ions that will still give you information about the end groups without the need for selecting a specific precursor with a 1 Dalton selection. But for that,
Yeah,
you need to
that might be pretty
some
challenging.
separation in the LC level.
It might be pretty challenging to get that kind of separation.
Yeah,
But,
so I looked
don't know
into I looked into getting standards for the tosylated version. We certainly, so everything we're doing here is external to Dow. So this is not a product offering from Dow, and so I could buy it. I didn't think it was necessary for the study that we had. You know, you can do. There is a chromatography. Is like I can't 100% remember the name. It's essentially a isocratic method that utilizes temperature to subtly pull out each distinct difference in the end group, and it's very sensitive to temperature. It's very sensitive to the composition of mobile phase. So we did consider different chromatography. I would challenge, you know, changing the pH that you're going to pull out, you know, ammonium or amine ends versus peg ends based on pH. These are 10,000 molecular weight. You know, and ACN versus methanol. You know, I really doubt you're gonna have, you know, enhanced separation. I think we could make it better by doing some different things, but I don't think you're ever going to get 3 or 4 distinct peaks out of this.
But you mentioned your instrument is capable of ion mobility. Why don't you use ion mobility? Because when I see that structure of the tosylate, the N groups are bulky. So you're going to see differences in the mobilities, in the drift times. So, and you can use that either without LC or as a second dimension to LC.
And then if you have the IM cell on, and if you activate ions in source, you can line up which fragment comes from which parent ion. So that will help you actually to correlate fragmentation and parent ion with the IM separation on.
The tosylated should be much larger at the same mass. So
I tried to do ion mobility, Chris.
Yes.
You know, when you're working, so you got to remember ion mobility on some of these commercial instruments reduce your ion intensity substantially. So you're looking at these and you're analyzing these already at low levels. You're throwing away your signal. So first I would say I've done it, you know, LC ion mobility, but you don't pull out these things. You can't see them. I can't even comment to say whether, I would also argue to say that if chromatography can't separate the tosylated and the amine, I'm not sure that an ion mobility is going to either. So next, I would say is direct infusion, you know, doing that, you know, I've also tried that experiment. And, you know, I've looked for the areas of these masses and you can't pull it out. And so there's some additional software applications that we're going to try to maybe see if we're missing it just from like a visual standpoint or where it is. But there are some challenges with ion mobility that come with this. You know, you got to realize this is a hybrid methodology with, you know, many moving parts. And so to incorporate another aspect is possible, but it just adds another layer of signal loss or complexity.
That's true. And especially if that's a minor product, then yeah, that's it works in some cases, like with surfactants. We showed that you can add ion mobility and you can increase the number, the resolution from LC to twice pretty much. That was Jason O'Neill's, who works now with David Dabney. But I agree with you that if you go to 7,000 K polyglycol, you may not be able to pull the amine. But what John can do is what was suggested before, buy the reference compound and check first would be the drift times different of having ditosylate versus
yeah, that's a good point. I thought the other aspect would potentially be, you know, looking at NMR, you know, to really sit on some of those aromatic protons or aromatic carbons. They should stick out well. You know, but when you're balancing, you know, the composition of the paper and what you want to include and where it's going to go, that was a follow-up experiment if the, you know, the reviewers thought it was important for that. So.
Oh, that's an excellent work the way it is. One more question that I had, I mean, is there any deconvolution software that you can use on top of that? So
yeah, I can, if Paul's on, he wants to comment, I can quickly. So we were going to write a section about deconvolution software, but the problem was the deconvolution software doesn't allow mixed modes of ammonium versus proton. And so I think the software that Paul uses is an open script one from Marty's group in Arizona. And so
deconvolution.
That's the one that we used also.
I mean, then it's not a deconvolution program. If it doesn't understand the combination of ammonium, proton, sodium together, it's not a deconvolution.
So, you know, when we ran the raw data through here, even with the charge reduced and the uncharged reduced, you know, the uncharged reduced, you didn't pick out anything new, and you were lucky enough to see like, hey, this is a blob around, you know, 10,000. You know, it's
I would agree with that. You could see in good cases where the deconvolution was working, it was accurate enough to pick out the right mass range, but not any compositional type of information beyond this is a EO repeating unit. So it was hard to pick out anything good when it worked. And when it didn't work because of mixed adducts, you know, it really suffered a lot. So I think there's definitely room to improve the performance of those, you know, for kind of what we observe, you know, in our data.
Those are, remember, written for the convoluting protein charges or biomolecular, which is usually protons. That's why. So we would need an algorithm that can take into account different charges. So you're correct. So that's a motivation for the computational people to devise such a program.
Another quick comment. You mentioned the impact of the mobile phase composition on the overall efficiency of the charge reduction. Do you have a way to use, for example, a reverse gradient, a second pump to do a reverse gradient? So start from methanol and go to water and mix the two in the end. So you have a constant half and half water methanol sent to the mass spec. That would probably at least so you like you know that you have the same efficiency of the reduction all the time, and that's no longer a problem or a variation that you may face.
So it's more of a problem with the polonium based, because as solvents change, the ion chemistry changes, and so we could do kind of like what you were saying, where you can do a reverse gradient. It's a little bit more challenging because you have the column, you know, dead zone, but you can rig it all up that it basically matches.
Yeah,
that works well. It works well. I didn't do it in this case. I don't know how much. My initial thought is, you know, 5 versus 10 versus 20 didn't seem to have substantial differences. You know, so it didn't. I didn't think to do that because it didn't seem to have deleterious effects. You know, if there was water present, it changed the degree of charge reduction. So I would actually try to push more to, if you could have an environment where you minimize the amount of water. So if you split it down to 5, and then you had a post-column addition where you made it like, you know, 15, and then you have a very small amount. You know, those are some of the games that you can play. But, you know, they have, in this case, I think sometimes when you do, you know, you move it to +4, +3, +2 versus +2 and +1, you're still getting a lot of the similar information. So it's kind of diminishing returns after a little bit. So, you know, if there was if there was severe complexity where you had things standing on top and they really start to spread out at 2 and 1, you know, that would be a length that I would go to try to manipulate it so there was as little as water as possible.
Thank you.